Okay, welcome back, everybody. This is the Virtual Residency Workshop 2023. It's Wednesday, June 28th. And this is our third session of the day. It's deploying community codes, and our speakers are Prentice Bisbal from Princeton Plasma Physics Lab and Stephen Wheat from Oral Roberts University. And take it away, Prentice and Stephen.
Okay, give me 1 second here. Okay. Hang on here. Google Docs doesn't like to play well with screen sharing, because then I can't see the screen, but I guess that's what we're gonna go with.
If you do screen reader mode where it looks like a little book open in the middle,
Okay.
then you can have both.
You do this much more than I do, apparently. Screen reader mode, where is that?
Oh, actually on Google Doc, I don't know. I would say do it with the PDF then.
Yep, let me just download that and do that. I actually have it downloaded. All right, guys, 1 second and we will get the show on the road. What I hate about PDF viewers that it always likes to add all these different things around your screen. Oh, that does the same thing. Okay, they both kind of do. Okay. All right, we're getting the show on. Uh-oh. Okay, here we go. All right. So just yell then. I'm gonna just do it in Google slideshow because I was having similar issues with the way I wanted to display in Google. So let's do this, share my screen. Can you guys see my screen? Is anybody there?
I'm not seeing it yet.
Not yet.
Okay, that's because I left out a step. Now you should be able to see my screen.
That's good.
Yep.
Okay, you know what? Now I can see everything. Okay, sorry about that, guys. I'm technologically incompetent. So thank you for coming today. I'm sure Henry's thank you all already. Me and Stephen Wheat are going to be talking about deploying community codes. And I'm going to handle part 1 and Stephen is going to handle part 2. I am going to be talking mostly about the fundamental basics of what goes on when you're building code and some of the things you need to understand. And then Stephen is going to talk about tools that can automate some of these and fix some of these difficulties, like using environment modules. In this case, I believe he's going to be talking about LMOD and using Easy Build, which is one of the tools that allows you to automate building code. I've been working at the Princeton Plasma Physics Lab for about 7 years, but I've been doing this role for about 25, and I have built thousands and thousands of packages over that time. I'm not saying I'm an expert, but I certainly have seen just about everything that can go wrong when this happens, and know how to deal with the issues, which we're going to be talking about a little bit here today, and what goes on under the hood. So, here's an outline of what we're going to be talking about. Won't waste too much time on this. So what are community codes? I always like to talk about terms and try to define them at the start of a presentation. So community codes are, they're programs of the community, by the community, and for the community, right? What does that mean? Well, they're written for a specific research community, maybe even a subgroup within a particular community. For example, within biology, there's systems biology or, genomics, stuff like that. And then there's probably even more specific groups even within genomics, like studying specific type of diseases or specific gene mutations. I don't know, I'm not a biologist, I'm just guessing. Here in what I do at the Plasma Physics Lab, we're doing plasma physics, but then within plasma physics, there's what we're doing, which is fusion energy and plasma physics here on Earth. And there's also astrophysicists that study plasma physics in stars. And so those are two different communities that both fall under plasma physics. Uh, so this code is often, these codes are often written by the members of the research community themselves. And of course, they're open source. Basically community code is another term for open source. And that's important because, by having the code being open source, the community can contribute to it in a variety of different ways, whether it's reading the source code and providing documentation, improving the algorithms in the source code, doing error checking and feeding that back to the developers. But that's really what we mean by community codes, right? So we're going to be talking about compiling code and why you need to do that, right? So part of this is historical, right? There in the past, HPCs on Linux, before Linux, or various Unix systems that we use for, this type of work. And a lot of the reasons why we historically needed to compile code was because of all the different Unixes. All the different Unixes use different processors. All the different Unixes came with their own set of compilers. All the different Unixes, of course, put things in different places or did things slightly differently. So that meant that there would be different library names or different locations of those libraries. On top of that, those libraries would be implemented differently, right? So even though they serve the same function, they might be doing things differently under the hood, may even have different APIs, right? So the arguments that you would, they may have the same function names or slightly different function names, or when you call that function, it's different arguments. And like I mentioned earlier, different paths to files, so things would need to be different. And so you couldn't just give somebody a precompiled binary that would work on every different Unix system, right? It's just impossible. Today with Linux, things are a little bit better. There's not as much variability. Different distros might provide different compiler versions, and those different compiler versions are going to have their own bugs, right? Or different distros might apply their own patches to enhance the stability, which may introduce unique bugs or behaviors. Although in theory that should not happen, but we all know theory and reality are two different things. Different distros may put things in different places, or at the very least call packages when you install them different names. There is a Linux standards base which seeks to minimize that, but it certainly still happens from time to time. To a lesser extent, but is it still a problem? Different processors. So we're going to need to compile things so the instructions are correct for that processor. Today, I probably should have listed x86 64 first, because that is still the most common one, but there's different versions of AVX support, right? Intel has had AVX 512 for a while now. The latest version of AMD processors finally have AVX 512 instructions. You have ARM variants, right? And the thing about ARM is that different vendors can extend the ARM instructions different ways. For example, what is it? Fugaku, the Japanese system, has ARM processors that are Fujitsu. I think they're called AF64X or something like that, or AFX64 processors. The Apple M1 and M2 processors, those are ARM variants that I'm sure have slightly different instruction sets. And then, of course, there's power processors. I'm managing a cluster now that's got Power 9 processors. I used to manage a Blue Gene that had ARM processors that were like embedded. There were power processors, they're a power processor, but from the embedded market. So they were power, but a completely different power than what I'm working with now. With the old Unixes, you had MIPS, you had Spark, you had whatever AIX used, you had digital Unix that used alpha processors. So you had a lot more variety of processors. So it's better today, but still not perfect. The other reason why we would need to compile codes is for performance, right? High performance computing is all about performance. So when we compile the code ourselves, we can make sure that it's compiled with the correct optimizations for our particular processors. If you take code that's optimized for AVX 512 and your processor only supports AVX 512, AVX2, you're going to get an illegal instruction error. And there could be other optimizations you want to make. Some codes, you can't make all the optimizations because rounding errors and stuff like that. You have to eliminate certain optimizations, and those might be different between different processors, how they optimize, that kind of thing. Precompiled binaries, you generally don't want to use these for HPC because they're typically compiled for the lowest common denominator processor so that they can be run anywhere. So that means they're probably going to be compiled for a 386 or 686 processor, or the lowest denominator of a 64-bit x86 64 processor. So the AVX extensions that I was talking about are probably not going to be supported, and that's where you get a lot of the performance on the newer x86 processors. You might want to compare the performance of code optimized for different compilers so you can see which compiler provides you with the best possible performance for your system, right? You might want to compare different implementations of the same library, which means you're going to need to compile multiple versions of that library. Now, related to this, you get into what is known as combinatorial builds. So that's when you're building the same software with a bunch of different versions of compilers or the libraries that that application relies on, or even building different versions of the same software so you can check for reproducibility between different versions, or catch regressions. And this leads to a lot of repeated effort and is a big, this is where a lot of our labor goes. So it's important you understand the steps of compilation. We don't need to go into detail, but you need to understand the basic steps. At a very high level, you have pre-processing, where the preprocessor pulls in the header files, also known as include files, and are often in directories named include. Then once the preprocessor does all its pre-processing, then it goes to the compiler where it gets processed and gets converted. And you have like the machine code files, the object files, which then get linked together in the final stage. Now, like I said, there's a lot of steps going on in the compiling phase. You have lexical analysis, parsing, all these other steps. We don't need to worry about them right now. They're not relevant to this conversation. So just ignore them. The important things we need to know right now are pre-processing, compiling, and linking. The reason being because these are where the errors are going to occur. And almost all of them are going to occur at the pre-processing or linking stage. Very rarely are they going to occur in the compiling stage. And the reason they're most likely not going to occur in the compiling stage is because that is just purely the language. And if the language, if the program was written to the standard, there's nothing that's going to change there. But the preprocessor needs to find the header files for the preprocessor. They're going to be in different locations depending on the Linux distribution you're using, and also whether you installed those libraries yourself to get like a later version, or that software isn't installed isn't provided by the operating system, or a third-party repo. So you're going to need to tell it where those are installed. And then when it links, it's going to have to do the same thing. It has to find the libraries you're referencing and link them together. So that's another source where it needs to know information or can't find things. And of course, the fixes for this are very easy. You either need to install the packages if they're missing, or if they're in a location where the build process isn't looking for them, you just need to tell it where to look to find them. I do want to point out that compile time linker and runtime linking, these problems are the same, but the compile time linker and the runtime linker are actually two separate things. And the reason I point that out is because there's two separate environment variables that dictate that they look at. And like I just said, errors rarely occur during the compilation phase. When they do, from my experience, it's typically because there's a bug in the compiler, or the code might be written in a version of the language that's not supported by the compiler. For example, Fortran 66 is a very ancient version of Fortran that hasn't been supported by any of the compilers I know of for a number of years. I actually ran into a case about 15 years ago where somebody was compiling something and it was spitting out a bunch of errors because they were using Fortran 66 and that was no longer supported by the compiler. And I just checked, Fortran 2023 is the latest version. I don't actually think it's actually officially adopted yet, but if somebody's looking at the standard and trying to write for Fortran 23, I guarantee you that you're going to find no compiler supports it or it's buggy. And the other thing too is some of the compilers provide their own specific extensions to the language. And if somebody is using those extensions, it's probably not going to be compiled or work on a different compiler. If you get errors at this phase, unless you're a competent programmer, you're not going to want to touch these problems because you don't want to break the code, you don't want to introduce errors, and it's a lot of work. These other errors with the preprocessor and linking are relatively easy to fix, and these are things that, as you know, system admins are in our wheelhouse, or just end users using the code. They're relatively easy to fix. So next, I want to talk briefly about the file system hierarchy standard. It's important to know this to a degree because this will help you find where files should be. And when you're installing software, it will help you figure out where you should install software. This is a standard that's been around for over 20 years now. This URL is where you can download it. I think it pays everybody. It's worth it to spend an hour or two reading it. It's not hard reading at all. Worth your time. The important thing that I have here highlighted in red is this is almost like a religious battle between different sysadmins and even users. Where do you install local files? The FHS does not attempt to define that or set up any rules. There's user local, which by the default on a lot of software is where it tries to install. But then people have arguments. Does that mean it's local to your site or local to your machine? So some people argue that you should not have user local be an NFS mount. That should be physically on the local hard drive of the machine. Other people say, no. Local means it's local to your local site. Therefore, NFS mounting is perfectly okay. The file system hierarchy standard does nothing to settle that battle. One thing is that it's typically used for third-party software, whether it's you or commercial software. That's it. That's where it should go. It shouldn't go in user. It should go in user local. And opt is the same. Opt is very similar to user local, and you have people kind of arguing for both sides. From my own experience, I have found that a lot of drivers, like when I installed the Dell or HP specific drivers for their servers, those things tend to want to install an opt. So I typically try to use user local. But now I try to use, before we get into the details, now I try to use my site name. So here at PPPL, for stuff that's PPPL wide, I'll install that in user PPPL. And for stuff that's specific to a cluster, it'll be like user cluster name. Like I'm working on a cluster now called links, so I'll put the software specific to that cluster in user links. That eliminates any of the arguing over where user local should be. And it's also makes it easier for the users to understand how specific that software in that location is. So this is what the entire file system hierarchy standard documents. And if any of you give a printed presentation like this in the future, I highly recommend you don't try to duplicate this. This took me forever to get it readable because all these little elbow connectors, none of them ever wanted to be in the right place where I wanted to put them. And I must have spent hours wrangling this slide when I first created it. So you'll see there's certain things here that are color-coded, whether they're optional or whether they're Linux specific. But all these directories you see here are mentioned in the file system hierarchy standard. This is a lot to memorize. As somebody who's building software, I kind of simplified it, and these are the sorts of things you need to know. You kind of need to know, bin and sbin are where executables should be installed. Bin is for executables that are available and should be runnable by everyone. Sbin means system binaries. Those are basically commands that are used for system administration type tasks. but that doesn't mean they can only be run by system administrators. Some of them you can still run, but they're as a regular user, but they're not really everyday commands that your regular user should be, so they're separated out. Now, like I said, you have your include directories, which your preprocessor is going to be looking into for the header files. You have lib and lib64. Eventually, I think you're going to see lib64 go away, and we're just going to have lib. But right now, I'm sure a lot of you know that you can still install 32-bit binaries even on a 64-bit system, so that you can have support applications that might only be available as 32-bit still. So you have lib and lib64 to differentiate them. And I'm looking at what's in user, but you see here at the root, you still see the same thing. And then opt and user local has similar structures underneath it. Oh, what happened there? Okay, I don't know why this slide got hosed up like that. So I'll do my best trying to remember what's below what you should do. So environment variables are variables, specifically, they're variables whose values are available to children of the process where they are defined. That's really all an environment variable is. You can define a variable and then child processes can access it. But they can access it, but they can't change it. It's different. How you define an environment variable is different from shell to shell. In bash, you use the export, well, in the Bourne or bash, you use the export command. With C shell and its derivatives like TC shell, you use the set env command for set environment variable. It's customary to use all caps for variable names, but it's not required for something to be an environment variable. Using all caps for variable name does not make it an environment variable. I've encountered people like, inexperienced users who thought that was the case, and that's not. Programs need to can check for the values of environment variable to determine how they should act. For example, path is a well-known environment variable, and that tells programs where to look for executables that when we type in a command, it looks to find the actual executable that on the disk that relates to that. The linker, the runtime linker, will look at LD_library path to determine where to look for the libraries it wants to run. You might have application-specific environment variables that might enable or disable verbose error messages to the screen, stuff like that. Here's an example showing the behavior of an environment variable versus a non-environment variable. You can see in this example, I'm using var1 and var2, and they're not in uppercase. Just pointing that out to make it clear that the name is not case specific. So I define both variables and then I export variable one, var1. Now, you can, in bash, you can do this all on one line. You could say export var1 equals whatever you want to set the value to. In the Bourne shell, which is the precursor to the bash shell, you have to put export on a separate line. So if you ever look at old init scripts or scripts that need to be run as root, a lot of system level stuff may used to and may still do it. I haven't looked recently. Use the Bourne shell syntax rather than bash, just because it's more universally applied. Bash will understand Bourne shell, but Bourne won't understand the newer bash capabilities. So here you see I define these two variables, export one so that it's an environment variable, and then I start another bash shell. So this is a child process of where I define the variables. If I do echo var1, you see that you get the result. For echo var2, you just get blank because the variable is not set there. Now I redefine var1 in this child process, and then I export it, and then I exit, and now I'm back at the parent shell. But if I do echo var1, you can see it's still what its original variable value is, because a child process can't change an environment variable of the parent process. And then I do, echo var2, and you see that it is still defined, but it wasn't available to the child process. And this is important because well, never mind, I'll begin to that later. So again, here's some common environment variables. Path, that's where, sorry, I see someone put a note, whoops. So path, like I said, your shell and other programs will look at that to determine where they should look for the actual executables you want to execute. Home is your home directory. Shell is your login shell. I believe it's only your login shell. So if you're running TC shell and then you run bash and then you try to check the value of shell, it's going to give you your login shell rather than your current shell. I believe. I never tested that, but I know there's something weird about it. I believe that's it. Library path will be used by GCC for your compile time linker. I specify GCC because I'm not sure that's universal across different compilers, but I know that's the case for GCC. And then you have LD library path. That's used by ld.so, which is the Linux runtime linker. So when you run a program, if it's not in the default locations, it will look in LD library path to find where those libraries are. Mike, I see your question. Afterwards, a question and answer, I'll address it there. And then, of course, there's Python path, which is where you specify where Python should be looking for additional libraries. There's a lot of others. These are just a few common ones that you'll probably see on a daily basis. So environment variables, the bottom line, when building and installing software, you may need them to tell the build process where to look for files needed by the build process. And after software is installed, you'll almost always need to define some environment variables so that you can find and execute the software. If you're not putting it in an existing bin directory, which for this type of software you probably aren't, you're going to need to add the location where it's installed to your path. You're going to need to install, if it has, libraries, you're going to need shared libraries, you're going to need to add the path where those libraries are installed to your LD library path so that you can run them. And then again, you're also going to need, might need to specify environment variables so that the software works the way you want it to, whether it's like verbose output, how it's logging stuff, what default behavior is. A lot of software has that. And the only way to really find out what environment variables an application is looking at is to read the documentation. And sadly, I find a lot of documentation doesn't list all the environment variables, and you often only find out when you run into a problem and you're trying to debug it and you contact the vendor or you post something in a user's mailing list and somebody says, oh yeah, you need to set this environment variable to have it do that. So when you're installing software, you need to think about how you're going to lay out your software. And what I'm going to show you now is a way of managing software that the LMOD people from TAC, the Texas Advanced Computing Center, used to say, how to organize your software. I don't think they said to put it in user local, but under where you install stuff, this is kind of how you want to do stuff. So we'll be using user local as our top level directory, and then each application is going to be installed in its own directory under user local. And then there's going to be a directory with the application name and then a separate subdirectory with the version name. So by the path, we can easily tell what version we're using. The installation directory is often referred to as a prefix, which you often have to specify when you're configuring your software build. And for the sake of this example, we're only going to be looking at building an application with multiple versions of MPI and then multiple versions of that application. There could be much more combinations than that, but then it gets really hard to fit on a slide in a readable way. So here's this hierarchical software tree structure that I described in a previous slide. So over here we have GCC, and we have 7.3.0 and 8.1.0. Now we have GCC-7.3.0 and GCC-8.1.0. This was the way TAC recommended doing it, and this means software under here is built with that particular version of GCC. all this software below this point in the tree, whoops, let me go back a slide, is built with GCC 7.3.0, and everything under this branch of the tree is built with GCC 8.1.0. Now, there's other ways you can do this, but this is just the way TAC recommended it. I looked at it when I was creating these slides. It seemed like a very logical way of doing things, so I've kind of adopted it myself. So here we have OpenMPI. Now, this is OpenMPI itself, which is why there's no dash here, but then you see the version numbers underneath it. And now we have OpenMPI-3.1.4 and OpenMPI-4.0.1. And then so the app 1 and app 2 versions underneath OpenMPI-3.1.4 were built with that version of OpenMPI. And then these versions of the app built with OpenMPI-4.0.1 are built with that particular version of OpenMPI. As you can see, if there were other dependent libraries that you wanted to vary, for example, you want to use different BLAS libraries like the netlib version and then OpenBLAS and maybe AMD's libflame and whatever the other one is called, or MKL, you could easily create many different versions that you have to build. And so here with this particular application, we have a couple of different versions, but you can see how that can quickly multiply. And you have, you could quickly have hundreds of builds to do just to install all the versions of the application you want. And I'm not even really talking about all the different dependencies that you would have to build and their dependence, the things they depend on, and so on and so on. So here on this slide, I highlighted the different things to make it a little easier to understand the logic here. This is compiler, GCC is compiler independent. Then you have the OpenMPI compiler dependent OpenMPI. Then you have the MPI dependent applications below that. Again, this is just one way you can organize your software. The important thing is that you pick a logical way to do it that you can remember and understand and that your users can remember and understand. Many ways to organize your software. Like I said earlier, the file system hierarchy standard doesn't dictate a way to do it, but you should find a logical way that both you can understand the logic and your users, and that's consistent and you stick with it. Again, we talked about, I mentioned the installation prefix earlier. It comes up all the time. And here's some examples of installation prefixes from my previous slide. Now, when you build software, most open source software has some sort of auto configuration tool. The most popular ones are GNU AutoConf and CMake, but there are others out there. If you don't have an auto configuration tool, if the package does not have some kind of auto configuration script, you typically, have to go and edit make files and understand all the variables you need to set in the make file yourself, or there'll be documentation on what you need to change and where. The way these different tools work is pretty much the same under the hood. They'll try to pre-process some code, compile it, link it, and or execute small code snippets to determine various things about your environment, whether it can find the header files and whether the information in the header files is correct. They'll determine, what functions a library provides. So different BLAS libraries, some might be 100% consistent with the standard. Some might not have all the functions that are part of like the full BLAS subroutines. Some of them might not accept all the same arguments as another does because it's an older version or it's a different implementation which deviated from some sort of standard. Sometimes they want to know what the executable output is, like ELF or some other standard. And then if they can find and link all the libraries that they need for their application. Now, you don't need to create these scripts. They're all done for you by the people who develop the software. You just need to know how to run them. So we covered a lot of this before. Oh yeah, the other thing I forgot to mention is that what these things do is they create the make files with the right settings. So then you just run make on them and compile all the code. We can do autoconf. This is by far the most common thing I see in most open source in open source software. To run the script, it's like it's just a script called configure. So you just go into the source code directory where you untard the source code and do a /configure, and then it handles everything. But there's various arguments you can add on the command line. And so what you want to do is use a configure -- help to display all the available options for the package you want to build. And you're going to want to pipe that in the less so that you can scroll through, because some of these will have hundreds of options, or at least hundreds of lines of text describing all the different options. And this makes it very easy for you to specify things at build time, where to look for the particular libraries, stuff like that. So this, in the old days of Linux Journal, I don't know if they still, use this term. They used to call this the open source 5-step, because these are the 5 steps you would use to install software. After you download it, you would untar it with tar. You would cd into the directory that you just created with all the source code. When you untarred it, you would run /configure, make, and make install. Now, if you do /configure without any options, it will install in user local, and it will just install it with the default settings and stuff. So this is, in many cases, if you're installing on a standalone machine and you only want one version of the software, this will work. I generally don't recommend it, because when you go to delete the application, its libraries are going to be in user local lib. Its include files are going to be in user local include. Its binary is going to be in user local bin. And so you're going to have to manually go through and delete them. Whereas if you put in user local application name /version or application name -version, whichever you want to use, you can just delete that whole directory and know everything is self-contained within there. So here's the issues with this 5-step. Doesn't specify a prefix, doesn't specify any other configuration options. A lot of times now, where you run configure and make should be separate from the actual source code directory. You often want to run make check so that you can verify that the code is operating properly. Not every application is going to have a make check function. That's up to the vendor, the developer's vendor, to do that. Sometimes it's called make test, but usually it's make check. And you don't want to be, so make install, when you install the code, it usually needs root privileges. Since you don't see a sudo in front of this last step, you're either installing it in your home directory or running all these steps as root. You don't want to do that. You only want to run the last install step as root. That way you don't accidentally delete files or break things when you make a mistake or typing a command that can have catastrophic effects. So here's a better example of the 5-step, which is now 9 steps. So you want to, unzip the application, go into the directory, make a separate build directory that's a subdirectory of that source code directory, cd into it, and then do that /configure, which tells it to look in the parent directory for the configure script. You give it a prefix to tell it where you're going to run it. And in this case, I'm defining CC, which is typically an environment variable, but you can define it right on the line like this so that it's available to the program you're going to run, and telling it I want it to use GCC as my compiler. And then this 2 greater than and &1 says tie output stream 2 to output stream 1. And then I'm piping that all to a T command, which is writing it to configure.log. That 2 greater than &1 says redirect standard error to the same location as standard output. And then that sends them both to that pipe symbol. And then I'm using T to write it to a log and also display it on the screen as it's happening, so that I can watch what's going on in real time, but also have a log of it in case I want to refer to it later. And then I do the same thing with make, and then make check, so that I have logs at every step of the way. And then I also, now here you see me doing sudo make install, and I'm doing the same thing to combine standard error and standard output. and there should be a T in that command, which I missed. But that now gives me logs of every step of the way. So if I need to go back and find out if there was a problem with my script, I can do that. But it also allows me to see in real time what the build and compile and make process, is all doing. So here's a more detailed of a configure command that provides more stuff. And these are things I commonly do. I define the prefix. I disable the silent rules, which is a newer feature you see in make scripts or configure scripts. And what that does is makes the make process spit out verbose messages about what it's doing. If you don't disable the silent rules, you'll just basically see like statements about what percent it's completed at that point. I don't like that because it makes it harder to troubleshoot things. So I disable the silent rules. You may have a different preference. I typically try to enable shared and static libraries because sometimes other applications aren't designed to, they're not set up to work with shared or static libraries. And I find it's just easier to build them both at the same time whenever possible, so you don't have to go back and rebuild the package once something that depends on that won't work with shared or static. And I like to be explicit about that. So because you can't always, not every application will build them both by default. So I like to be explicit. So when I check my notes, I know, yes, shared and static should have been built. And then with foo, this with foo option is typically if you want to have an additional feature that may not be by default, you typically got to say with foo. And if you don't have the equal sign, it's going to, and of course, foo is just a stand-in for whatever the option is. Again, you need to do /configure -- help to see what the options are. If you don't add the equal sign, it will typically just search in default locations. If you add the equal sign, you give it the path to where it's installed so it knows where to look. Here I'm specifying I want GCC for my C compiler and G++ for my C++ compiler. The environment variable CXX is typically used to denote your C++ compiler. FC is your Fortran compiler. Here I'm specifying G Fortran. F77 is the environment variable is typically a capital F and then 77. And here I'm using C flags, which specifies the path to the include, and LD flags are for the linker. These are flags that are expanded in the make file to expand to the search path for the linker. This is different than library underscore flags and LD underscore library underscore path. C flags is specific to GCC. Other compilers may use it, but I know it's specific to GCC. But you will find that sometimes other compilers honor GCC's settings and environment variables just because it's so ubiquitous. So CMake is another configuration method. It's not popular as a GNU autoconf configure script, but it is a very healthy second place. There's really nothing very common after those two. Like auto configure, the developer needs to set it up and provide it for you. It basically offers the same functionality. You can configure options. It creates make files with the correct settings. This does require a separate build directory. If you try to run CMake in the same directory as the source code, it will complain. And you use the ccmake command to get a text-based user interface for specifying commands. You can specify things on the command line, but there's no -- help option like there is with autoconf configure script to show you all the options. So this is what it looks like when you start ccmake. This is what the text user interface looks like. And you can use the arrow keys to go down to these different options and turn them on or off or define the values for those variables. And here's the process. You need to run C to do the initial configure setup. So once you do ccmake and you see that TUI that I showed you previously, you run C to do the initial configuration. and then you go through the options, set them, and then you run C again, and then you press G, which will generate the new config, the new make files, and then exit, and then you do a make check, and then a sudo make install just like before. Now, when you're done with the build process, now you need to define environment variables so that one, users can find the application in their path and run it. And then on top of that, they need to have environment variables set so that they can look for additional software that they need to run, or again, to define specific behavior you want them to do. So there's a couple ways you could do this in the old school way before we get to environment modules and what Stephen is going to talk about. So there's two ways you could do it in the old school way. You can have users add this to their RC files if they want to use the application. And there's pros and cons to that, mostly cons. You have to communicate to the users what to set. That's either an email announcement or putting it on a web page that you use to document the software in your environment. Both of those, users tend to not read those on a regular basis, so you're going to run into issues. Every time you upgrade, you can either install to the same location, which means the users won't have to update their scripts because everything is going to still be in the same place, so the same environment variables are valid, or you're going to have to tell all the users to update their RC scripts, which is all the same problems you have with communicating what to do in the first place. Now, if a new version is installed to a new location, the good thing is users can still, if you keep the old version in the old location, users can continue using their old version if you don't update the script, if they don't update their RC files. The problem with that is that, with this, is that only one version can be used easily, right? If you want to switch versions, you got to edit your RC scripts, log out and log back in for them to take effect. Now, in Etsy profile.d, as a sysadmin, you can put a script there that will set the environment variables for that application. It will happen on login time for all the users. So that means there's only one place for you to make changes. You don't need to communicate that to the users. The problem with that, though, is that you got to have a separate file that makes those changes in the syntax for the different shells you use. So born in bash shell, you're going to have a .sh file that does that. For C shell, TC shell, you're going to have a .csh file that does that using the C shell syntax. Z shell, I don't know enough about to know whether it can use born syntax or if it has its own syntax, in which case you might need to have a third file. If you make changes there, that can surprise users when they log in and now it's calling a different version of the software they weren't expecting. This again only allows a single version to be usable. And this again takes effect on login. So a user has to log out and log back in order for these changes to take effect. Now, there is an easier way to do this. You have environment modules, right? There's two of them. There's environment modules and there's lmod. And what they do is a user can quickly run a command like load and then the module name, which will include the application name and the version name. And it quickly changes their environment to suit the needs of that application. And then they can unload that module and quickly erase those changes without having to edit RC files and then logging out and logging back in. And it allows users to quickly switch between versions. So if you're compiling something with GCC and then you want to build it again with Intel, you could do that very easily. And there's probably not the best example because since the commands don't overlap, you could have both GCC and Intel in your environment at the same time. But generally, you don't want to have multiple compilers installed because when you're configured at the same time, because when you do a configure, you don't know what compiler that configure script might find first. If you're explicitly compiling code on the command line because you're a developer, that's not as big a problem. The great thing about this is it's shell independent. So you only have to have one module file that defines those changes for that application, and it will work across all the shells. You can also use it to make sure that mutually exclusive settings are not being made by your users. This can be a problem where users are loading different modules that really shouldn't be loaded at the same time. One quick example is if you have MPI for Pi that provides its own MPI, and then a user might also have MPI, some MPI implementation module loaded at the same time. That can be a problem because now you have two different MPI implementations loaded in your environment. And when you run MPI exec or MPI run, you may not be getting the MPI you expect. Like I said earlier, there's two main environment module applications in use now. Environment modules, which is older and more traditional, and LMOD, which is developed at TAC, and Stephen's going to be talking about this. It's written and implemented in Lua, but it understands all the old environment module syntax. So you can write module files for environment modules, and they'll still work with LMOD. LMOD has a lot of additional features. A lot of people that use it swear it's far superior to environment modules, and they never go back. Now, we talked about combinatorial builds and how work can quickly grow exponentially once you keep adding more and more packages to your build process or combinations. So the old way of doing this was just basically taking good notes of your build process so you could cut and paste your previous commands, make whatever changes you need, and then run them again. Time-consuming and tedious. There's new ways. There's two different applications that automate this. There's SPAC and Easy Build. SPAC is a DOE project that was started, I think, Lawrence Livermore or Lawrence Berkeley. And then there's Easy Build, which I believe is its development efforts are based in Europe. I don't know much about it. Stephen is going to be talking about that next, so he can go into more detail. And that's it for me. So brief intermission for the few seconds it takes to switch over to Steve. And I see there's been some questions and comments. I think we should save questions till the end, and I'll look at the comments and maybe address them during the question and answer time. Stephen, I don't know if you prefer Steve or Stephen. I turn it over to you.
All right, thank you, Prentice. I presume everyone can see the presentation slide here.
Yep.
All right, excellent. So I'm Stephen Wheat. I'm a professor of computer science here at Oral Roberts University. I've been here for 5 years now. Before that, I was at Hewlett Packard Enterprise doing system solutions for HPC for a couple and a half years. Before that, I was at Intel for 20 years. And before that, at Sandia National Labs, and before that, at Bell Labs. So I've been in high performance computing for 41 plus years, and glad to be here to talk about this. We'll be focusing on the Easy Build environment, both from how to deploy the applications and then how to use Easy Build as a user. There's quite a bit of stuff here, but it's intended that this presentation is a rigorous script of how to go about the deployment of Easy Build, and a little less rigorous on how to use it, but the examples will show you why that is, because it's a much easier type situation. So the thing I do not get into is in network file system. I presume people that are going to be deploying Easy Build would already be familiar with NFS server and client setup. We just take advantage of that. Absorb what you can with the presentation, but the presentation is posted, and I did set up a virtual machine and walk through every step of this to make sure that there weren't any lies, but I still could have missed something. Anyway, let's proceed. So the motivation here is we want to be able to deploy applications either for one specific user, but without having to use their user environment and whatnot, because they eventually may not be the only user, or more users is typically it. We want to install applications without rebooting the compute nodes. This is really about focused on how to provide these applications for a cluster environment where when you launch a job on 10, 500 nodes, you want them all to have access to that application and its an environment. You don't want to go off installing it on every single one of them, especially if it's a diskless node where you don't want the virtual file system being bulked up by a bunch of images that the user may not be making use of. We also facilitate the ability to have different versions of the same software. Updated versions come along, as you know, but here we manage the ability to have several versions simultaneously available, and a user can make use of the version of their choice simply by loading the module of their choice. The last bit here is a little bit of a tongue-in-cheek: install complex applications with minimal effort. Most of the time when the word easy or simple is used, it's anything but easy or simple. But in my humble opinion, in this particular case, easy build kind of sticks to the easy side of things. So anyway, so we'll proceed. So our assumptions here is that the OS dependencies, there are some going to be applications will need additional libraries. And so, for example, you're wanting to install a given application and needs OpenSSL. And that is something that's going to need to be, the libraries, system-like libraries, it's just typically easier to deploy them on all the compute nodes. We can kind of predict which some of them are going to be, and in the easy build configuration setup, I take note of, let's have these libraries pre-installed on compute nodes so that you don't have to, when you're building and deploying a new application, you don't have to reboot the systems on all the compute nodes to be able to take advantage of that application. Here we're going to assume that all such dependencies are already installed on the OS nodes, but we'll still kind of call out which ones are frequently seen that need to be installed on the compute nodes beyond a baseline compute environment. CPU architectures. We're going to assume here that the cluster is configured out of, built up out of a single CPU architecture. Then assume that the build node, where easy build is going to be used, is of the same architecture and generation as the compute node. So yes, we can have Intel architecture, we can have ARM and so on. And Intel architecture clearly has all the different versions: Sandy Bridge, Ivy Bridge, Ice Lake, blah, blah, blah. And so you get into those details there. Here we're just presuming an homogeneous environment. Same architecture, same generation. Here at ORU, we actually have the same architecture. It's Intel based, but we have 3 different generations. We have 3 different easy build hosts, and we have 3 different NFS mount points for the easy build deployed applications. I'll be getting into that a little bit, but not for a single architecture. But we use auto mount to disambiguate which of those 3 that a given node needs to mount, and it all just works. If I'm running on a Sandy Bridge node, the right version pops up. Ice Lake, same thing. But here we ignore the auto mount and multi architecture work and focus on a single architecture to get that basically down. The rest of it is kind of rinse, wax, and repeat for the different architectures. For those, we just saw some things about environment modules, so I'm not going to hang on that too long here, but the intention is that we're going to be setting up an environment that the tool is going to, for a given user, when they want to load a module, it's just setting up their path and their LD library path to include the software package that they want to run, and it does it rather cleanly and transparently to the user, so they don't have to deal with the details. So I'm going to give, for those who've not used modules before, and whatnot, I'm going to just do a quick live, you know how dangerous that is to do, demonstration. And here, hopefully you see it. Yep, that should be what's shared. So I'm going to do a modules list. Oh, sorry, I don't know why I did that. Okay. No modules are loaded. And so it's a clean environment. And if I do, for example, echo my $path, we're going to find a fairly simple path. user local, and user SBin, and finally, my own home suite bin. But if I do a load of a module, well, first off, how do I know which modules I can load? I can do a module list avail. And it will eventually just list out a whole bunch of modules that we've pre-installed on the system for users to consider. And you can see that we have a variety of different versions. For example, we can see that Python, we got 5 or 6 different versions of Python there, Perl, Proj, Open, MPI. You can see it goes on and on and on, on and on and on. We got several versions of Fluent, and then we have different tools, and as well, the Intel environment is completely available there. The One API module environment is made available to the users as well. And so that just tells us what all is available. So if I now do a module load R, for example, it's going to load that module. And let's scroll back up here. If we take a look here, R, we've got 3 different versions of R made available. This one here is shown as being the default. So if you don't specify a version, which you can specify on that module load command, this will be the version that's loaded. So if you wanted the 410 FOSS 2021A compiler environment, you'd just say module load R/4.1, etc., and it would load that up. Now the R needs several other pieces of software to be installed. And when we do the easy build of R, it actually causes a bunch of those environments to be built as well. So other modules, we did not build each one of these literally by ourselves, individually. A bunch of them just came about because you said easy build R, and it had dependencies on various different versions of who knows what. And it caused those to get built and those modules to become available on the system as well. So that simple loading of R, remember when I said module list, there was it was empty. Now if I do a module list, 99 modules got loaded just to support R. So that goes kind of back to some of the comments that Prince has made, is that you've got all these dependencies of different things that when you're building software, you need to maintain those. Well, here, we didn't care about any of this when we built the R module. It just caused all these specific ones to be built. And when the user, like I just did, loads that R, it knows which of those modules to also load and bring them online. And now remember that path that I had before, that nice simple path. It's a little less simple. And so one of the things I would like to, so clearly I can run R here, just type R, there it is, that's R. But in any case, if I want to unload that, simplify my environment again. If I unload that, we'll find that R is not there anymore, but everything else is. And so if I want to, because it doesn't know, maybe I've got something else loaded that needed those, I can actually just purge all the modules I have loaded, whether I explicitly loaded them or implicitly. And I can just do that. And then if I do a module list, I'm back to no modules there. Let's see, purging, I'm using, running, etc. Okay, covered all of that for one examples. All right. So that was a live thing there. Now the modules architecture, because we want to have this available to all the compute nodes in the cluster, we're not interested in building these on each and every one of the compute nodes. So we're going to use an FS here, and we deploy in /opt. And we, as I mentioned earlier, We export that. We actually have 3 different directories for the 3 different Intel architectures that we support. And but underneath, you know, underneath /opt, the environment we have is we have opt/modules, which is where the Lua files are going to be put. Those are the control files for the object for the module. And then there's also /opt/software, which, oops, sorry, I can highlight that, /opt/software, which is the directory where the actual application is installed. And so for if I go back to my example over here, if I do an ls/opt/software, we'll see all the applications are there. And then the Lua files, which typically the user isn't going to care about, but anyway, the builder may care about. We have, oops, sorry, modules. There's the directories of all the Lua files. If we go into, for example, R, there's the 3 different Lua files for the 3 different versions of R that I showed earlier that are available. We also have, Intel made it relatively easy to install and integrate the One API toolkit underneath just /opt/Intel One API, and we include that in our module path. I don't cover how to do that here, but we might do that in Q&A and take a look at that. So, presuming you're starting from scratch, we're going to have on a server that is of the same architecture as the compute nodes. It's going to be that easy build environment. We're going to install the things that we need to be able to use for that easy build. So to do that, we need the basic LMOD environment. I have found it easiest to be able to do that by leaning on the OpenHPC repo. And even if you're not using OpenHPC, you have other ways to install the LMOD environment, but this one is these 4 lines. Get the repo, install the DNF plugins, enable your power tools if you haven't already, and then install LMOD-OHPC. And your LMOD environment packages is set up, and you're ready to go on your compute node. It should be on your build node. A similar thing you would do for your compute images. You may have different environments than we've got. We use the OpenHPC recipes, and with Werewolf, others use Ansible and things like that. You got to get the LMOD environment onto the compute node images as well. But here, because we do the Werewolf approach, we do the same command to install the repo and the LMOD OHPC with the Chroot environment for the image that we're building for the compute. So once we're ready, we need we typically will set up and not build the modules, the applications as root. We set up that we want to have these directories. We want to have /opt/modules all, and we want that, and the opt/module/tools, and we also want to have a user, not root. And so we create a user, we specify which user ID it is. You can go about that however you want to go about it, but we allow it to be in the group root. And we add the user, and then we set up the directory, and we chown it to be owned by EasyBuild. Remember, we're running all of this as root right now. And then to be sure, if it's not already installed, we go ahead and install Python 3. And again, this is on the build environment. All right. Now, both on the build environment as well as on the compute nodes. These are some things that we find are useful to have already pre-installed because easy build scripts for the given applications may be looking for these tools to be in place. So OpenSSL, OpenSSL development, the development tools, and then the RDMA, especially if you're in an MPI environment with an InfiniBand or OmniPath or whatever fabric, the RDMA core development is frequently referred to in some scripts. With all of this in place, those particular things on that build node, everything's been put in place to be able to do modules. We go ahead and edit at this point the lmod.sh inside that was installed in profile.d when we installed the lmod dash ohpc. And we say to know about the easy build directories we set up. Its default is to have just a simple, very short module path. Here we just add to that module path as a colon separated additional directories, colon opt modules all, colon opt tool. And if you have the Intel environment, you do a colon /opt/Intel/1 API, and that will work for whenever anyone logs in with the with bash as their shell. It'll work. If you want to do it for C shell users, you do the same modification, but with the setenv as Cryptis mentioned earlier in the lmod.csh file. So we're good to go. It's there. It's available for people. It's going to be people log in now. They'll be able to see the modules because that's they set this up. And by the way, there's a presumption here that we're on the login node as the build. If you have a different login node, then it's going to also need to have the Lua environment installed. We don't need these commands, but we do need to have the lmod ohpc installed and have that on the login. But if the login node is the same node that we're using to manage the easy build environment anyway, it's already been taken care of. Let's see here. So the actual building, we are somewhat following this. There's a web page here, and it's, I refer to it all the time for remembering how to go about this. We issue to easy build, and then we have to install easy build. And the first step there is we need to install a temporary version of easy build because we're doing an easy build to install easy build. The easy build's not there yet, so we're just going to do a temporary local install of easy build and /temp/$user eb_temp, and then we do the pip install easy build following this particular syntax. We're telling it to put easy build into that EV temp directory. Once it's there, easy build is usable from that particular spot, but it's a temporary type situation. It's not in our /opt/modules location. Then we do it for real. We create ourselves a config file. You don't have to absorb all this here. We're just going to walk through it, but we create a config file in the easy build. Again, we're logged in as easy build, and that config file is going to have, the way we set it up here is much of this is commented out. It's not there, but the modules tool we identify as being lmod. Our prefix for actually building the applications. The applications are built in the user easy builds directory .local/easybuild. Our install path gets set up to be /opt, and our install path modules is going to be found in /opt/modules. So that simple config file adopts the directory hierarchy that we have set up already with the creation of those files and directories. So we've got the temporary version of easy build installed in that /temp. So now we go through these 5 commands here. We're going to set up a environment path to know about where EB is. We're going to export the Python path for that script to know where is it. And this is all one line. Sorry, I didn't put the backslash and continuation, but that's all one line. And then we export EB Python telling the easy build script that we're using Python 3, which is in our path. We've installed it as we mentioned earlier. And then all we do here is we just say EB space -- install latest EB release. And that will populate the easy build module in our module environment. And once it's done, it doesn't take too long. You'll be able to just ls/op/module/easy build, and you'll be able to see the Lua file for the easy build. And now the EB environment is in our actual easy build Lua environment. So once that's done, we're going to log out and log back in as easy build, just to flush everything out, get rid of those path modifications we did earlier to use the temporary version of easy build. We're going to issue the easy build module avail, and we're going to see that among other things that may be there, the easy build 4.7.2, if you do it relatively soon, that's the current version, is the default, and you're going to find it in /op/module/all. And so that's all set. And then let's see here, we've been through this already. And so now we get to actually use easy build to build an application. So once again, we're going to make sure that we're as easy build as the user. We're going to, this is important, we're going to purge all defaultly loaded modules. That lmod.sh that we put in profile.d causes some modules to be preloaded for every user. We're going to purge that because we don't want anything to be loaded versus our system compile environment that we know about, so that the scripts do not get using to where they're going to be using, say, some compiler version you didn't intend to use when you're doing the build. So it's good whenever you're going to build something, we're going to just purge, and then all we're going to do is load the easy build module. We're going to say module purge and module load easy build. Now we get to see, well, what's available for us to build. And so we've got this command here. For example, I want to say, hey, I need a GCC environment, a different version of what I got. What GCC environments are available? I can do an EB-S GCC. If you don't pipe it to this grep command here, you'll see a lot of different listings where GCC is used in the names of other modules, and you'll just see a screen full of useless information. So this allows it to settle down and show you what is actually available. So I'll do, nope, sorry, can't do that here. I'm not logged in as easy build, never mind. So this EB-S will find that, we'll find that this is the latest version of easy build. And we're just going to grab that, and EB GCC 13.1.0.EB, that whole string will just cut and paste from the, or copy and paste from the listing of the modules that are available to be built. And we're going to do a -- robot. That tells it to, if it depends upon other packages, for it to download, install, and install those modules as well. And this particular one is a bad example because it takes a while. And it'll populate several additional modules. And following the same kind of thing, if you want to build and install OpenFOAM, you can go search for which OpenFOAM versions there are. And here I just give an example, build this version of OpenFOAM, and off we go. And you just walk away, go to lunch or whatever, go to dinner, go to bed, whatever. And these things to do. All right, so that brings us to the end of setting up Easy Build for users to make use of. We walked through some of the uses of Easy Build as a user. I was logged in as a user. So we're going to open up for a Q&A. And what I'm going to do is, while we're doing that, I'm going to actually go to an easy build environment to show you that dash S environment, because there's a little bit of subtlety where this string comes from that I wasn't prepared to show live, but I'll get there while we're talking through the Q&A.
Any questions, anyone, for either of us?
There are lots of questions in the Zoom chat.
Yeah, I went through those and I believe I responded to them.
Okay.
All right, so I'm on my Ice Lake easy build system. And we're going to look at the GCC one, the grab. And we'll see all the different versions of GCC that can be built. You can see it's the configurations as a shell variable to set up to show where it's going to be finding these. G is for any tool that starts with G. GCC is the base name of the tool. And then we have these different versions. And so this is where that GCC 13.1.0.eb, that's the string we snarf and just say eb paste that -- robot, and off we go. Not going to do it. So that's one thing that I wanted to demonstrate there. And if you want to do the same kind of thing with 4 of the various different versions of R that are available to be pre-built, we can see these versions of R being available. And by the way, easy build is the environment, what's available, what's this -s is finding, the scripts that others have gone through the brute force thing that Prentice described and capture all this and built up the easy build scripts to actually build these things, and they eventually publish them. Every so often it'll release a new version of easy build. And back to, let me go back on showing this, and then go here. If you want to install the latest version of easy build, just log in as easy build, load up the module easy build, and tell it to install the latest easy build release. If you already got the latest release, it won't do anything. If there's a new one, off it goes. That release now becomes the default version. You would log out, log back in, load up easy build, and do your easy build -s to see what version. Oh, someone done a newer version of R, for example.
So Stephen, there's a question. Can a regular user, not an admin, install easy build in the cluster?
Ooh. For single, I presume that's a question for a single user to make use of an easy build environment for themselves, not worry about others per se. The answer to that is yes, you can. You can set it all up to where it'll do all the builds in your /local, for example, and it should be .local within your home directory. It'll build everything up. You can set up the that config file that I mentioned before. Instead of pointing to /opt/modules, you would point to twiddle username /local/modules, and you can have your own set of modules. The only thing you can't do is if you need, for example, that OpenSSL environment set up as, on your system. Well, now you need sysadmin to get that made available. But otherwise, yes, it'll build. Easy build is just another user. We give it the root privileges so it can go look at other directories during the build process. That so far I personally haven't found that that's a necessity. So yeah, and if you then export your .local, twiddle user /local modules environment, if you make that publicly readable by other users, and they set up their LMOD path to look there, they'll be able to use your modules, your applications as well. And as that, your /home is usually mounted up on the cluster, you'll be able to use it on compute nodes as well, and those others. Now, some places, Henry, correct me if I'm wrong, but I believe that when I go in and log into Oscar, the only home directory I can see is my home. Is that correct?
I'm sorry, the only home directory you can see what?
Is my own.
So it depends on file permissions, but so some users set their file permissions somewhat open or entirely open. We don't generally allow them to have it world writable, but especially their .ssh directory, but some people have their directories open, others do not. So I would say the answer is you can see any home directory that the owner set its file permissions open.
Okay, all right, fair enough. Same,
But
same here then.
I would say as a system admin, please don't do that. Just because what happens is you get an entire department or organization reliant on software running out of a user's home directory. And then they expect us to support it, or that person leaves and now the entire organization comes to a screeching halt. It is good to use tools like Easy Build for software where you're going to use, or if you have a specific project, you could configure it to build software in your project directory so people of your project could use. But ideally, if you're going to be using software that multiple people are going to need, talk to your system admins and have them install it in one central location. It ultimately makes life better for everybody.
I do want to, that's a good point. What you can do is not necessarily what you should do. I want to go into this. Oops, see, can't go in there. Well, anyway, I was going to look for an example. One of the things that I wanted to remember to point out is that you don't necessarily have to, you know, for example, we have the, oh, well, I'm going to back up altogether here. We also build up and deploy home built applications inside our modules environment. It's not done by Easy Build, but just as you can build, as Prentice was showing earlier, through CMakes or configure files and so on. For example, we maintain Gamus here. And I just set that up as another module in the module path. And my chemistry professor gets to just module load Gamus and off he goes. And you don't have to, if you're going to be running Gamus, you don't have to type in module load Gamus and then run your SBatch script. You don't have to do that. You can put the module load inside of your SBatch script. And all it's doing, again, is just setting up your path and your LD library path and a few other environment variables set up to control that environment. And in the Slurm environment, those environment variables are exported to all of the compute node login images that you have. And so they all adopt that environment, and you get yourself, you know where Gamus is on all those compute nodes. So you can just put the module load, whatever module you need, into the SBatch scripts. And if you're going to be doing a bunch of compiles and you want a particular version of GCC, you can put the module load, the appropriate version of GCC inside your .bash_profile, and just choose which of the modules you want. Of course, if you decide you want to change which one live, you can just load a different module. Okay, my clock just chimed. Henry, I think we're at the time.
Yep. In fact, we're a little bit over. So let's give a virtual round of applause to Prentice and Stephen. We're going to take a short break. We'll be back in about 14 minutes. And then Prasad Madhumaj will be presenting debugging, profiling, and tuning. So let me stop the recording here.